Welcome back to week 2. We're going to continue with elementary graph algorithms. In the last lecture, we saw breadth first search. Now, I'm going to talk to you about depth first search, the next most popular graph traversal algorithm, and one application of it which helps us to find strongly connected components in graphs. So unlike breadth first search, depth first search goes deep down a graph. Starts from a source vertex, takes one of the vertices that is adjacent to the source, then looks at another vertex that is adjacent to the child of the source vertex and goes down and down and down. When there are no more vertices to explore along a path down from the vertex S, depth first search comes back and looks at other vertices in the adjacency list. So it explores the graph in a depth first way, unlike breadth first search, which explores the graph in a breadth first way. So as I told you, DFS explores edges out of the most recently discovered vertex V that still has unexplored edges leaving it. Once all of these edges have been explored, the search backtracks to explore edges leaving the vertex from which V was found. This process continues until all the vertices that are reachable from the original source vertex that we started out with, they've all been added as reachable vertices, they've all been found or discovered. And if there are undiscovered vertices that stay back, DFS starts all over again from a new source and repeats the search. This process goes on till every vertex is found, and like breadth first search, you can prove a theorem which shows that depth first search discovers every vertex that is reachable from source, and if you reset the source, it will discover new vertices that are reachable from source. It doesn't give you shortest paths like breadth first search, but it gives you a whole lot of other useful properties of exploring vertices in the graph. So depth first search returns a forest of depth first trees. By looking at the pi attribute like we did in BFS, you can populate the trees, and the edges, that double colored edges that we saw like in breadth first search, will be called as tree edges. So same like in BFS, we color the vertices. There we colored it white, blue and black. So here also it's to start with it's white. Then it can get an intermediate color, let's say gray color or a blue color. And when it's finished, it gets a black color. So when it's not yet discovered, it's white. To start with, all vertices are white. When it's discovered for the first time, it gets colored gray or blue. And when it's finished, it gets colored black. Along with color, we also assign timestamps. In breadth first search, we assigned a discovery timestamp, which measured the distance in terms of the number of edges. Here, we also assign a finished timestamp. That is, we assign a discovery timestamp to indicate the step at which the vertex was colored from white to either gray or blue. That is when the vertex was discovered. And then we assign a finished timestamp when we are finished with exploring that vertex fully. That is when that vertex finally gets colored black. Obviously, a vertex should first be discovered before it is finished. So for always, it is the case that the discovery timestamp is strictly less than the finished timestamp, and totally these timestamps can never be more than the number of edges, and it's never more than twice mod v. So to start with, before it's discovered, as I told you, a vertex is white. When it is discovered, it's assigned gray or blue color. When it's finished, it gets assigned black color. So again, what I'll do is I'll walk you through the algorithm. The slide, I put it as one image, but I will illustrate a few steps of the algorithm on this graph, and then we can understand the pseudocode. So let me keep the whiteboard adjacent to this so that we can copy down the graph and then see what it is. So the graph that you see here at this point, right, that's your source graph. So how many vertices does it have? It has 6 vertices. So let's copy down the graph here. So that's one vertex, that's one vertex, third, fourth, fifth and sixth vertices. So they are labeled U, V, W, X, Y, Z. As you notice, it's a directed graph. So edges have directions in them. By the way, both breadth first and depth first search will work for directed and undirected graph. It doesn't matter. It's the same algorithm. I hope you're all clear about that. So let me just copy the graph for you from the slide onto this whiteboard. So that's it. This is the graph. So now we have it. So let's move the whiteboard to the center before we go back to the slides and illustrate a few steps of the depth first search. Right, I'll keep this little bit of the slide popped up on top so that you can see what is happening. Right, so let's say this is my starting vertex. This U is my starting vertex. So I begin my depth first search from here. This is my vertex. So this is my start vertex. So I assign a discovery timestamp. Discovery timestamp is 1. That's what is put inside the label of the vertex. So I have discovered it. So I'm going to put 1. Because there's not enough space, I'll write it outside. Now, I look at how many vertices are adjacent to the vertex U. There's an edge from U to V. There's an edge from U to X. I can pick up any of them. It doesn't matter. Let's say I pick up V. So what I do is I take this graph and the next edge that I choose is this edge. So I'm going to double color this edge. And this is the next vertex I pick. So I'm going to assign timestamp, discovery timestamp 2 to this. Now I start looking at the adjacency list of V. There's only one vertex going, one edge going from V to Y. I don't have much choice. So I pick up that edge, put it onto my tree and assign discovery timestamp 3 to Y. Now I look at the adjacency list of Y. There's only one that goes out of Y. So I assign timestamp discovery timestamp 4 to Y and then I put it in my DFS tree. Now I look at the edges going out of X. There's one edge going out of X into the vertex V, which has already been discovered because I have assigned a discovery timestamp. Strictly speaking, I should also color, but because I'm managing with the same graph, I'm not coloring. So this I don't consider, right? So if I don't consider, then what do I do at this point? Basically, I have reached a point where I have reached a vertex from where there are no new outgoing edges to new vertices, right? So what does it mean? That means I'm done with exploring that vertex. So I say I'm done with exploring X. So I assign a finish timestamp to X, which is 5. And say this edge that I found here, this edge is a backward edge. I'll tell you what a backward edge is, but let me color this B. Okay, sorry for the very colorful example, but it helps us to understand. So now I go back. I came to X from Y, so I go back. I now look at the same thing, do the same thing. Look at the adjacency list of Y. Anything left? No. X is there. I finished exploring X. Nothing left in Y. So I say I finished exploring Y also. So I assign finish timestamp to this. So by the way, I can now color X and Y both as black. I'm not illustrating here. So I go back like that. Now go back to V. Anything to be explored out of V? Nothing. So I assign a finish timestamp to V and I move on like that. So let's lower this whiteboard for now. Go back to the slide and see where we were. So DFS goes on running like this. We were here. And at this stage, we assigned a finish timestamp to X, where my mouse is. This is the copy of the graph, which is marked F here. After that, I'm also done with exploring Y. So Y is colored black. I assign finish timestamp to Y. That's this graph marked in G. Then I go back to V. I've finished exploring V. V gets colored black, gets assigned a finish timestamp. At this point, I go back to U here, the graph down below here, and I look for, are there any more edges? Yes, there is one edge which goes from U down to X, but X has already been colored black. So it's not a new vertex that I'm finding. So I say this kind of edge is what we call a forward edge in DFS because it is an edge that connects the vertex that I had started out with originally to an already finished vertex. So this is an edge. As an edge, it's called a forward edge. So I say, oh, I basically found a forward edge. There's no more new edges to be explored from U. So I color U black and assign a timestamp. So I'm done with these 4 vertices. Now I come to this side. This graph actually has 2 more unexplored vertices that are white in color. I can start all over again. I can consider one of them as the source. Let's say I consider W as the source. So I assign a discovery timestamp for W. The next left number I've used up till 8. So now I say discovery timestamp is 9. Then I repeat the same thing. I go from W to Z, finish exploring Z, color Z black, discover, finish Z, come back and finish W. That's the easy way of doing depth first search. So I'm basically exploring adjacency lists, but I'm exploring them in a depth first way. I go down and down and down and down, picking up one vertex, successor vertex in the adjacency list instead of going in a breadth first way where I pick up subsequent successor vertices. Now we are ready to look at the pseudo code of DFS. So the procedure is called Dfs of G. It takes a graph G and first what does it do? For every vertex in the graph, it assigns, it colors that vertex white. It assigns its parent to be nil and says, now I need timestamps. So it keeps a variable called time to keep track of timestamps. Initially, it says time is 0. Now, what it says, now you take any white colored vertex as your source, let's say that vertex is U, and start this routine called DFS visit from that source. Let's look at what this procedure DFS visit is. So DFS visit is going to do DFS on the graph G with U as the source vertex. The first thing that it does is increments the timestamp variable by 1 and says for the vertex U, assign its discovery time to be that value of the timestamp and color U gray, that is lines 2 and 3 for you. Start exploring the adjacency list of U, exactly like we did in breadth first search. For each vertex in the adjacency list of U, if you find that its color is white, set its parent pi attribute to U, which is used for computing that tree. And this style of writing this is slightly different from the style of writing breadth first search pseudocode that we saw in the last lecture. Here, it recursively calls DFS visit again from V. So what will it do? It will start exploring in the next call of DFS visit. It will start exploring the adjacency list of V. And if it finds a white colored vertex, it will make V as its parents and call DFS visit from that vertex once again. When this for loop ends, it will come and say, I have finished exploring the adjacency list of U completely. So you color U black, which means I am done with exploring U. Increment your timestamp value and say that is the finish time of the vertex U. So line 9 increments the timestamp value and line 10 assigns it as the finish time of U. I hope this algorithm is clear. This is basically what we saw in this example. So like BFS, DFS also takes linear time. Why? Because there's a initialization loop and after that the for loop runs once for every vertex as long as there are vertices in the adjacency list. And the vertex color of the vertices progressively go from white to gray to black. They never get recolored. So at most it's mod E. So the running time of DFS is linear in the size of the graph, which is mod V plus mod E. Again, now we have a few theorems that talk about why DFS is correct, what are its properties and all that. I have kept them in the slides for the sake of completeness, but I'm not going to go through the details of all these theorems. Basically, the first theorem, which we call the parenthesis theorem, says that what we saw earlier, right? A vertex is first discovered and then it is finished. So the discovery time is always less than the finish time. And if I mark the discovery and finish times properly, then they look like pairs of nested parentheses. So if I take the interval between when a vertex U was discovered and when a vertex U was finished, and if I take the interval between when a vertex V was discovered and when the vertex V was finished, if the two intervals are disjoint, then U is not a descendant of V and V is not a descendant of U. They cannot be reached from each other. Whereas if the two intervals are such that the interval for u is completely contained within the interval for v. Let's say u was discovered at timestamp 3, finished at timestamp 6, and v was discovered at timestamp 1 and finished at timestamp 8. So interval 2, 6 is within the interval 1, 8. Then it means that u is a descendant of v in the depth first search tree. And the third bullet is the reverse of that. So you can check it out for this example, and for proofs refer to any standard textbook on algorithms. One of the reasons needed for correctness of this thing, DFS. Then there's a white path theorem which says that when I first look at a vertex v, if I'd started DFS from a vertex view, when I first look at a vertex v, I basically have a path of white colored vertices from the vertex u to the vertex v. Then this is one thing that I briefly told you about. The vertices that get into the tree are the vertices that you use for traversal. Those are the tree edges, the edges that get into the tree are the edges that you use for traversal. Those are the tree edges. If I find a forward edge, that is, if I end up reaching a vertex that is already colored black through another adjacency list exploration, then that edge becomes a forward edge. Back edge are those that connect an ancestor back to a descendant back to an ancestor. And if it doesn't belong to one of these three categories, then we say that the edge is a cross edge. Yeah, so if the graph is undirected, our example, the graph was directed, but if the graph is undirected, then I don't get forward edges and cross edges. I only get tree edges and back edges. Yeah, so that was depth first search. It was a quick module. Feel free to ask me questions when you're revising this, or refer to any standard book on algorithms if you would like to know more about DFS. But from the point of view of testing, you could just pick up, you could just pick up any routine that implements DFS for our purposes later in the course. One more algorithm that will be useful for you that's related to graphs, which we will need for the purpose of the course, is to understand what a strongly connected component is. So let me go back to the whiteboard and draw an example for you. So I'll keep this aside and illustrate strongly connected components. So we'll take an example of a graph. So let me just draw a graph. Please excuse my not so great handwriting. Strongly connected components are defined for directed graphs. If a graph is undirected, then you call it a connected component. Okay. Let's label these vertices u, v, w, x, y, z. So this is some graph G. So what is a strongly connected component in G? Let's go back and look at the definition, then we'll come back and see it in this example. A strongly connected component of G is a maximal set of vertices such that every pair of vertices, they are reachable from each other. So remember this definition, let's go back and see. The strongly connected component is a maximal set of vertices. Why maximal? The largest set possible. I'll illustrate it on that example. Such that within that set, C, every pair of vertex is reachable from each other. So let's go back and see. So let's take this strongly connected component and let's start with a vertex U. So I claim, now let me mark, I claim that this part defines one strongly connected component. So C1, first strongly connected components, consists of vertices U, V, X and Y. Why? If you see U is reachable, when V is reachable from U, there's this edge. U is also reachable from V. You go to V to Y, Y to X, X to U. Similarly, U is reachable from X through this edge. X is also reachable from U, right? You can go U to V, Y, V to Y, Y to X. So all these four vertices are reachable from each other. Now, why I didn't put W as a part of this blob If you see, W is reachable from V through this edge, but is U reachable from W? Answer is no. Try. You can go from W to where the only vertex you can go out of W is W to Z, and then you can come back to W. There's no way I can reach U or V or X or Y from W. So W doesn't belong to this strongly connected component. For the same reason, Z also doesn't belong to this strongly connected component. In fact, this is the next strongly connected component, this one. Because between W and Z, they are reachable from each other. So C2 is W and Z. So strongly connected component is a maximal set of vertices. Like for example, V, X and Y is also a strongly connected component of size 3. It has 3 vertices, but I can find the larger strongly connected component of size 4. So it's maximal because it's as large as possible. So it's a maximal set of vertices such that every pair of vertices within that set are reachable from each other. So the nice thing is you can run depth first search as a subroutine to illustrate all the strongly connected, to pull out all the strongly connected components of a graph. So the algorithm that uses depth first search to generate strongly connected components in a graph uses the notion of a transpose of a graph. So let's see what that is. Transpose of a graph G is basically you retain the same set of vertices. Keep the graph V as the same set. For edges, if I had an edge in the direction from V to U, okay, change the direction of the edge. Take a graph, keep all the vertices as they are. For every edge, change its direction, then you get the transpose of the graph. If you see, this takes a bit of thought. If you see, the original graph and its transpose will have the same set of strongly connected components because the same things will be reachable from each other. Strongly connected components means what? Reachability both ways. It's like that's why it's called strongly connected. It's reachable from both ways. Transpose, I'm not changing anything except for the orientation of edge. So graph and its transpose will have the same strongly connected components because reachability both ways will be preserved. So this is the algorithm for strongly connected components. So you first take the graph, run DFS on the graph. DFS outputs what? Tree of DFS, a depth first search tree. It outputs the start, discovery time, finish time. So what step 1 says is run DFS, remember finish times, the F attributes for each vertex. Then take this graph, compute G transpose. Just take the adjacency matrix of the graph, take the transpose of the matrix, that will give you the transpose of this graph. Flip the direction of each edge. Now you run DFS once again on the transpose of this graph. Okay. Now don't choose vertices in any arbitrary order, but in the main loop of DFS. Let's just go back to the DFS code for a minute. I'll go to that slide. So this is the main loop of DFS, this one. Here you say, no, each vertex in the adjacency list, which vertex you choose, if there are more than one, it's up to you, it doesn't matter. Based on which one you choose, you might get slightly different DFS tree. But in this, to compute strongly connected components, what do? Second time when we call DFS on the transpose of a graph, in that main loop that I just showed you, you don't consider arbitrary order, but you consider vertices in the order of decreasing finish times. Finish times as computed in line 1. Okay. Now you will get DFS trees for line number 3. It so happens that each such DFS tree will be a separate strongly connected component. That's what it is. So again, a few lemmas that will tell you why this is correct, but I'm skipping through them because this will increase the length of the recording lecture. But again, feel free to refer to any standard book on algorithms or get back in touch with me if you'd like to understand the correctness of this algorithm. But remember, this is the critical part. Bfs and Dfs are two graph traversal algorithms. Bfs enjoys the property of giving you shortest paths. Dfs gives you discovery and finish times. Dfs can also be used to compute strongly connected components, which are like maximally connected loops in the graph. So in the next module, what we are going to do is directly start looking at some coverage criteria on graphs, and I'll tell you how later on we are going to use these algorithms to generate test cases from graphs that we are going to consider for testing. I'll stop here for now. Thank you.